In this video, we're going to do another example of simplifying resistor networks, which can be simplified with series parallel combinations. So let's say we have a battery of voltage V, and we want to know what resistance that battery sees, or what the equivalent resistance is attached to that battery. So if I were to make this circuit look like this, a battery and a resistor, what would that resistance value look like? What would it be? And let's say that all of these resistors have a value of R. I'm just not going to draw it so that the diagram isn't cluttered. So how do we start this problem? Well, remember that we need to find a weak spot in this network. And so we need to find at least one set of resistors that can be added together. And so it looks like there's a couple candidates, but I'm going to start with these ones on the right. So there's 3 resistors here, all in series. And so we can replace them with a single resistor of value 3R. And if you're doing this, I recommend that you actually redraw the entire circuit because it'll greatly simplify your life. So, okay, we've got that resistor. I think that's all we can do on this side for now. It also looks like these 2 resistors here are in parallel with each other because they're connected at this end on the top and they're connected at this end on the bottom. So I'm going to simplify those. Because they're both value R, their equivalent resistance is going to be R over 2 because they're in parallel. So I'm going to replace these with a single resistor of value R over 2. Now, I also see 2 resistors down here which can be combined. So these 2 resistors are in series because they're connected at one node and nothing else is connected at that node. So I'm going to replace these 2 with a single resistor of value 2R because it was 2 resistors of 1R in series with each other. And now that we did that simplification, it looks like this resistor of value 2R and this resistor of value R are also in parallel because they're connected at this end and they're connected at this end. So if I want to add them in parallel, because there's only 2 of them, I can just use the formula 2R times R divided by 2R plus R. So that's R1 times R2 divided by R1 plus R2. And so this is 2R squared over 3R, or 2/3 R. And so I'll replace these 2 by a single resistor of value 2/3 R. 2/3 R. And now you're starting to see we're making some serious progress. So now these 2 resistors are in series with each other. So we've got an R over 2 plus a 2/3 R. So that's what? The common denominator is 6. So we've got 3/6 plus 4/6. So that's, well, can't do math, 7/6 times R. So we can replace these 2 with a single resistor of value 7 over 6 R. Now, you might think at this point, well, it looks like we're kind of stuck. Because our voltage seems like it's stuck here and there's no more simplification that we can do. But it looks like this resistor on the left and this resistor on the right are actually in parallel because they're connected. They're both connected at this end and they're both connected at this end. It doesn't matter that there's something that's also connected between them. So even though they're on opposite sides of the circuit, we can still combine them in parallel. And so we can use the formula, so 7/6 times 3 over 7/6 plus 3. And that's the end result is going to be R because they're in parallel. And at this point, we call in our calculator or Mathematica cavalry, and we find that the answer is 21 over 25ths R. And so we can replace this one on the right, or we can delete this one on the right, and this one, our new value is 21 over 25 times R. Now, this one is also kind of tricky to see because it looks like these 2 resistors are in parallel, but they're actually connected at just one node, and there's nothing else connected at this node. So these two resistors are actually in series. And so their resulting value is the sum. So 21 over 25 plus 1, which is what? 46 over 25? 46 over 25R. And we can delete this one. So this is our equivalent resistance. We've finally simplified it into this diagram on the right with a voltage and a single equivalent resistance. And it's on the left, but that doesn't matter. It's the same exact circuit. And so remember, to solve this, we first found a single weak spot in our network, and then we simplified it, and then redrew the network, and then we repeated it. And we repeated it until we were left with just one resistor. Finally, I'd like to thank all my patrons on Patreon. Your support is greatly appreciated, and it is you who makes these videos possible. If you aren't currently a patron, to get early video access, behind-the-scenes footage, exclusive content, and join a like-minded community, click the link on screen or in the description below. Thanks for watching.